Welcome in today's lecture in the lecture series Explainable Machine Learning, and today we will talk about local model agnostic methods. We already had 3 lectures and this is the 4th lecture. And as in each lecture, let me first start with a little bit categorization. So what are we talking about and what are we, what do we want to do today? And as in the last lecture, we can distinguish explainable machine learning methods by specificity. And so we are specifically looking today into local model agnostic approaches. And using such approaches, you want to understand how the model relates the input to the output without having access to the model. So maybe you do not even see the model, or maybe you do not have access to some of the model components. Doesn't matter. Some part of the model is a black box and you cannot access it. So what you want to do is you just want to understand the mapping, and that means what will happen to the output when you change the input. And this is what you can see here. And we already talked in a previous lecture a bit about the second part here, but today we focus on this. And the last time we talked about approaches to interpret the whole model behavior. That means for all data samples, for the whole data set. This can be done, for example, by calculating a prototype. We also talked about prototypes. And a prototype means a maybe syntactic typical instance which will lead to a maximum score, or which will tell you something very typical, very representative for the whole data set. We also talked about which features in the data set are most important for a decision. Today, we will look into approaches to explain individual outputs. And that means a specific decision. So we will focus on the first part, and the last time we talked about the second part. And when we talk about local model agnostic approaches, this will give you insights about characteristics of one specific sample. And I want to briefly repeat what attributions are. And for more details, I refer here to the last lecture. I just want to briefly repeat it so that you know what we are talking about. So attributions tell us how much an output is influenced, positively or negatively, based on changes in the input. And what you see here, this here, is a model that might be non-transparent. That means it's a black box model, that's why it's illustrated in black. You see data instances with several feature dimensions, so this is illustrated here. And you have some output with like a regression output, that means a continuous output, or a class output, that means you have a discrete output. And these illustrated data instances here, so that means one box is one data instance, and the numbers represent the data, that means the features. Today we will have a look at feature attribution and also pixel attribution, but first of all feature attribution for single instances. Feature attribution, for example, looks at specific features like a specific type of measurements, like for example, one dimension if you take a hyperspectral measurement. And very often this is referred to feature importance. We also talked about this in the last lecture. You talk about feature importance in case you assume that the change in the output when changing the input is the importance of the feature. And this can be done for single instances and the whole data set, and today we focus on single instances. That's why this plot changed a little bit from the last lecture. So what you see here is only one feature dimension and one specific sample. And we will also have a look at pixel attribution. And there's a very, very close connection to feature attribution. Actually, it's a special case of feature attribution. And so pixel attribution is also sometimes called saliency mapping or heat mapping. And it is a special case of feature attribution where important pixels in images are identified, and mostly for one specific image, one specific instance, it means one specific image. So illustrated here is we are not looking at specific feature dimension. It's more that now we are looking at a spatial part in the image, one important part in the image, which is responsible for a specific output. So let's start with one first specific example. So let's first have a look at the feature attribution, and then we go to pixel attribution. It means to saliency mapping and heat mapping. So, but let's first start with feature attribution, and here I want to show you Shapley values. This is a super cool method with some really nice properties. We will talk about the properties in a bit more into detail in a few minutes. But first of all, what are the goals of Shapley values? So Shapley values determine the contribution of each feature of a single prediction to the output by calculating the difference between the actual prediction with specific feature values and the average prediction. And this is one really crucial part, and I will repeat this several times. The reference here is the average prediction. And so what you analyze is, you analyze which feature is responsible for a change from the average prediction. And its theoretical basis lies in game theory, and here you can see one nice image from the inventor of the Shapley values. And as you might assume, he's called Mr. Shapley, specifically Lloyd Shapley, and he received in 2012 the Nobel Prize for Economics. And one part was, or a part of this, his whole work were also the Shapley values. So let's have a look what Shapley values are. And illustrated here is a very simple schematic overview about all the components we need for the Shapley values. So assume you have players in a coalition. So you want to play a game. And all these players play together. That means they play in a so-called coalition. And a coalition is an alliance for a combined action. So you play together, not against each other. And you play together one game, and you have an overall payout. And now the question is, what is the assignment of a payout to each player based on the contribution? It's assumed if you have a larger contribution, you should get, or you have a bigger assignment of a payout. But yeah, we are not working in game theory, we are doing data science. So when we will transfer this now to data science, we have this scenario. So what you have is you have a set of features which with given values. These are your players in a coalition. So one feature is one player. Then you have a prediction task for a single instance. This is your game. And you have an output. This is your overall payout. So this is the real estimation, the output you get from your machine learning model, from your prediction task. And the question again is now, what is the contribution of each single feature to the overall payout? That means to the output. Okay, so what the Shapley value actually is the weighted average marginal contribution of a feature value across all possible coalitions. So let's assume we want to know the contribution of one player. In this case, the yellow player. It's yeah, you can think of a player, or you can also think about the feature. In this case, it's a feature phi d. So we have a look at one specific feature of a single instance, and we need to compute the contribution to all possible coalitions and average them. So this whole computation is a very comprehensive computation. So what we need for it, we need to decide in what we want to analyze, and we need all possible coalitions. Okay, coalitions again are sets of players or features. So when we have, let's say we have a set of 4 players, and now we want to analyze the contribution of the yellow player to all the other coalitions. What you need to know is how many coalitions and what possible coalitions are there. And here illustrated are 8 of them, all possible coalitions. So what you have is you have the full coalition of the rest 3 players. You have an empty coalition, so it's when the yellow player would play alone. Then you have 3 different types of sets. You have 3 sets where each of the set has 2 players, and you have 3 sets where you have only 1 player in it. So you have 8 coalitions with given feature values to which the yellow player contribute. Actually, it's called green player, but it's a yellow player. So the challenge is now, as you said, we are not in game theory, we are not playing, we are doing data science, and the challenge is a machine learning model cannot be evaluated with less than d features. So it's not that you can just here take out a specific feature dimension and then analyze what happens. This is not possible. It would be possible if you train separate models for each number of features, but computation is super expensive, and also you do not want to have different models for the computation. You want to have one model in this, and you want to analyze the decision process in this specific model. So you need an alternative. The alternative is that the feature values in a coalition are fixed, and the feature values outside a coalition are randomly sampled from the dataset, so they are treated as unknown. This is a very common procedure that when you want to get rid of the effect of one part, one feature, you treat it as unknown, or you want to treat it as unknown. So you randomly sample again and again and again. And this is the effect of marginalizing out, or this is called marginalizing out the effect of other features outside the coalition. So if you take one feature and you compute again and again with random samples or randomly sampled values of this specific feature, it's marginalized out. And this marginalization is illustrated here a little bit more. So let's assume again you have a yellow player and you have your coalition of 3 players. And so this is one scenario. It would, this would work. But what if the red player is not playing? So what to do? You do not want to compute a new model. You want to get rid of the effect of the red player. What you do is you compute here, or not really computing. You select multiple outcomes, or you select multiple values of the red player, and you compute multiple outcomes with these typical values, and you average them. So you get rid of a specific value of the red player. What you do is you just test everything what can happen. So you marginalize out a specific effect of the red player. And let's have a look at how the Shapley value can be computed for a single prediction. That means a single input sample. So this equation might look a little bit complicated, but we can through it step by step. So first of all, what we want to compute is the Shapley value for feature D. So, and what you can see here is, for example, this S here is the coalition, the subset. So as I said, you have several ones of them. D is the total number of features in, that means the grand coalition. In our case, we have 4. This D with the exclamation mark afterwards is the factorial. That means the factorial of 4 is 4 times 3 times 2 times 1. So what else would we have here? This is sum over all coalitions without the feature. D of interest, so this is what you sum about. And then you have these 2 parts here in brackets. So the first part is the output after feature D is added to coalition, and this is when you remove it. So this is actually what you want to know. Depending on the coalition, what happens if the player is there or if the player is not there. That means if the feature can help with the estimation or it cannot help with the estimation. And then we have this one here. This is a little bit more complicated, or the whole term, but there is, so what it says is, so this term within the sum corresponds to the fraction of times S appears within possible player permutations, or you can also interpret it more intuitively. You can say it gives the highest weight to the most informative contributions of the player. And the most informative, or when you think about it, what's intuitive? What is the most informative contribution of the player? It is when already all players are there and you add it, because then you can analyze, does it have any added value if you already have a lot of players? That means the biggest coalition, or if the player plays alone. So, and this gives some weight. That's why it's an overall weighted a weighted sum. And so it analyzes the contribution of the player to all coalitions. But let's go a little bit more into detail, and I will show you one example, which is when we want to analyze the contribution of phi 1. So what is the contribution of phi 1 when you have 3 other features, phi 1 to phi 4? In this case, you want to analyze phi 1. And let's assume now, let's have a look at one specific coalition, and the coalition is phi 2 and phi 3. So this is actually only one part of this whole equation. So what are you going to do? First of all, step 1 is you add phi 1 to the coalition. So now your coalition contains 3 features. And so what's happened now is, what do you do with phi 4? So it's outside the coalition, but somehow you need to compute an output. You cannot leave it away. So you need this marginalizing out procedure. So what you do is you randomly sample from your set of possible values of phi 4. You take one sample, one positive, not one sample, one possible feature value, and then you compute the output. So now you have values for all the features, so you can compute an output. This is step 2. Step 3 is you remove phi 1 from the coalition again, because you want to analyze what is the effect of phi 1. But again, you cannot treat it or you cannot just remove it. So what you do is you also randomly sample from positive value for phi 1 to also marginalize out the effect of phi 1. So coalition again is now smaller. You have random samples for phi 1 and phi 4, and you compute the output. This is step 4. Okay, so step 5 is now you compute the contribution of phi 1 by comparing the output when the feature is in a coalition and when it's not in a coalition. And yeah, in order to get really this marginalizing out effect, what you need to do is you need to repeat the sampling for the feature values outside the coalition and average them. You can do it very comprehensively by taking all possible values, or by not only taking all possible values, but using all the whole data set. But mostly this is too time consuming, so you can restrict yourself to just, let's say, randomly sample for 100 times, depending how much time you have and how complex your data set is. Okay, so yeah, repeat this, of course, the whole procedure, and you do this for phi 1 and for phi 4. Okay, so let's come back to our equation for the Shapley values. And first of all, I want to emphasize again what we compute and what we not compute. What you compute is, or what the Shapley values do, is they explain the difference between the actual prediction with specific feature values and the average prediction. So the crucial part is here the average prediction. It's not the difference between the actual prediction and the prediction after it was removed from the model training. So for the first one, that means the Shapley values, or for the first item, it means the Shapley values answer the question why a specific prediction was reached in comparison to the average prediction. And for the second one, the crucial, or an add-on to the second item. So for the Shapley values, the feature set is actually really never changed. So it's not that you take something out. And you can relate these two things, what it is and what it's not, to the terms contribution and sensitivity. So the Shapley values compute a contribution, and the second one is more related to sensitivity. The difference is the reference, or you can, there are a bit more differences, but one crucial difference, what you can keep in mind, is the reference. For the first one, you have an average prediction accuracy of all possible coalitions, and for the second, there's no comprehensive or outside reference. So it's only analyzed what happens when you remove the feature and compare in comparison to when it's there. So what you analyze, it's the sensitivity, and the first one, the Shapley values, is really a comprehensive computation, and you compute the actual contribution. So this is a crucial thing, because also for the second part in today's lecture, I will more talk about sensitivity. And Shapley values have some nice properties. I already mentioned I mentioned some properties what we actually want to have for interpretation tools to be especially good, and especially good for explanation. And I want to mention 4 which are demanded when we talk about interpretation tools. So first one is efficiency. It means the sum of single Shapley values equals the value of the ground coalition, and the value of the ground coalition is the actual prediction. So this is fulfilled. Then we have the property of symmetry. The Shapley value of two feature values should be the same if they contribute equally to all collision. This is also fulfilled. Then we have the dummy property. That means a feature value that does not change the predicted value should have a Shapley value of 0. That's reasonable and it's also fulfilled. And then we have an additivity. Additivity means for predictions that arose from added prediction from individual models, the Shapley values of the individual models should also add up to the Shapley value that arises from the overall model. To give you an example, we have decision trees, and random forest is a sum of these decision trees. And suppose you trained a random forest, which means that the prediction is an average of many decision trees. The additivity property guarantees that for a feature value, that you can calculate the Shapley value for each tree individually, and then you can average them and get the Shapley value for the feature value for the random forest. So this is actually fulfilled, and this is a nice property. And so Shapley values fulfill all these four. This is not the case, or this is for nearly no interpretation tool the case. So that's why Shapley values are quite nice. And to give you one example, let's assume we want to map tropospheric ozone. Tropospheric ozone is a toxic greenhouse gas with highly variable spatial distribution. And the problem is that so far, the relation between geospatial data and ozone metrics are not well understood. So you might think, so what is the problem? The thing is, ozone metrics, everything related to ozone is very can also only be measured sparsely, and it's time consuming. But geospatial data can be easily acquired. So for example, with remote sensing sensors, imagine you can just have a satellite and you analyze this and you get an impression about tropospheric ozone, air quality and such things. That would be nice. So so that's why you want to do it. Unfortunately, so it's not so well understood so far, but fortunately, there are some research groups who develop data set for it, so that we can have a deeper look into this relationship and develop models which can relate this geospatial data with ozone values. And you can find the data set here if you're interested in it, so you can play around it with it. Just to give you a brief impression about the data set, so what was done is several features were collected, and so these are all the features used in this model for this relationship. And all of these features are more or less known for proxies for tropospheric ozone. So experts analyzed this and they said, yeah, there are proxies, and the output are accumulated ozone values over 4 years. And actually, what we want to know in this study is, can we assess the robustness, the scientific consistency, and the global applicability of the model? And for this lecture, I want to show you how you can use, in this case, Shapley values, to check the consistency. So if you learn a model, it would always be nice to see if the model really does what it should do. And what you need for it is, some interpretation tool and an expert. And we had both of them, and I will show you now the analysis. So let's have a look at two single predictions, a rural station in the US and an urban station in France. And the contribution of each of the single features are illustrated in so-called force plot. So you have two stations, you have the US station on the top and you have the French station on the bottom. And each of the single prediction has one force plot. So what you can see in the force plots is, first of all, here, there in the middle, you have a base value of 27.7 ppb, which is the average prediction over the whole training data set. So when you have a lot of predictions, you average them, and then a feature can increase or decrease the predicted ozone, and this is illustrated in red and blue arrow. But as I said before, you have this reference, which is the base value. Then you have two stations, so you have two final predictions for them. So one is 23.5 and one is 31.9 ppb, and it results from adding all Shapley values to the base value. So 23.5 is the final prediction for the French station, and 31.9 is the final result for the US station. So this is illustrated on the top here. The most contributing features are illustrated here and labeled with text, and the values are given. So not all features, but only the most contributing. And so the ozone station 8, the top one, is located in a rural area in the US with many agriculture fields and a smaller city nearby. And the average ozone at this location is predicted to be high, because the model uses the absence of forest, the low night light and 5 kilometer area value, and the absolute latitude as features leading to high ozone values. And it might sound weird, why is ozone high in a rural area and higher than in the city? But it's a fact that most of the times ozone levels are higher in rural areas than in city. And this is sometimes called the ozone paradox. The reason is that ozone can be degraded by other chemicals like nitrogen oxide, which occurs more in cities. So this does not mean that there's less air pollution in cities, but you have other pollutants there, so other pollutants are present, and that means not only present, but they have a higher concentration than in cities, but there's just less ozone. And the French station here is an urban background station surrounded by fields. And the location is further in the north than the US station, which leads to a strong decrease in the predicted ozone value. And that's why here the absolute latitude is used. And the low relative altitude further decreases the predicted ozone. And for further clarification, as I said, we consulted an expert. Altitude is the height about the sea. So first of all, the altitude is the height above sea level, and the relative altitude is the height above the lowest point in a radius of 5 kilometers. So one is more local and the other one is global measurement. And experts told us that might be a good proxy, both of them. And also we consulted these these air quality researchers, and they said both quantities are interesting, since ozone increases with the absolute altitude, and it makes a difference whether we are on a lonely mountain top or a high plateau. So, and we further consulted, and it so far it makes sense. And if you really have a look into it and you think about why this is happening, why this specific prediction is happening, you can actually find for each of them a reason, and it makes sense. I told you about a few of them, but if you would have a look at further measurements, further predictions, you can also see that it makes sense what's actually predicted there. So let's now come to or what I also want to show you here is it's not, as I said, we want to focus on the local methods today, but I want to show you that we can also take all the single prediction analysis and put it in or use it for a global analysis. And what you can see here is a so-called summary plot. And what you can see on the left is the used features as input. And right next to them is the global importance, which is the average sum of the absolute Shapley values. And the absolute Shapley values is what I showed you on the last slide. And if you perform it for the whole data set, you can get such a plot. And in this colorful part are the Shapley values for these single predictions illustrated in a B-swarm plot. Because from this you can actually quite nicely see the influence of some specific features. And as a side note, because you might wonder why not all features are illustrated here, here I only illustrated the features with more than 1% global importance. And the global importance of the features absolute latitude, altitude, relative altitude and nightlight in 5 kilometer area are highest with a contribution of at least 10%. This is what you can see. It's sorted from top to bottom. And the remaining features have a weaker influence on the model output. And for example, in the last row, what you can see is the influence of the climatic zone. And this can be, does not have really an influence on the result. And yeah, so the left plot reveals the contribution of the features to the prediction. And what you can see is, for example, in the first row, a low absolute latitude value leads to an increased ozone value prediction. So low feature values have a high contribution to the overall payout, which is the prediction. And what you need for this is actually this color here from red to blue. And then you can see or you can have a look at the specific Shapley values on what Shapley values are typical for low feature values or high feature values. So that's why also this B-swarm plot and the sum of the single prediction gives you a really good impression what features are important. And in the same way, for example, the higher altitude and the relative altitude increase the predicted ozone values. And the high nightlight and 5 kilometer area values lead to lower predicted ozone concentration. And we actually again checked with the experts, and these tendencies are in line with domain knowledge in the atmospheric chemistry, with domain knowledge on the atmospheric chemistry of ozone. Yeah, so this was an example. Of course, you can perform this with different data set, and all these data set will then give you hopefully similar core insights. So let's talk a bit about the advantages and disadvantages. I already mentioned these 4 properties, and it's a fact that most of the interpretation methods don't fulfill these 4 properties, but Shapley values do. And that's quite nice, because then it makes an explanation based on this Shapley value interpretation much more easier. Then what is also nice, Shapley values can take into account the whole data set or just a subset. So for example, you can, this is useful for analysis when you only want to have a look on a specific part of the data set. But it's oftentimes misinterpreted. That's why I said it over and over that the reference is the average prediction, and it's not then that you just take out the feature and look what happens. And also it's only reliable for data sets with a lot of features. With a lot of features, standard answer, it depends. How much is a lot? But you should not, or you might not use Shapley values for data set with only 3 or 4 features. Then you need access to the data set because you need to randomly sample, for example, from typical values. I say it because this is not always the case and is computationally expensive. They are efficient implementation, mostly tailored to specific types or specific architecture. For example, there are specific computation for tree-based method. And here you can have a look at this Shap library and this reference here. This is also where we take these plots from. So try it out, it's really nice. And yeah. Okay, so let's come to the second part. And here I want to talk about heat mapping with model-agnostic approaches. So here we go away from specific features of single prediction and we now go to images. Images are always nice if you have this as databases because it's much easier to highlight specific parts in an image or it's easier to understand, easier for interpretation and later explanation than a big data set. And I focus on one specific example, which is whale monitoring. I mentioned it already, and I want to go a little bit more into detail because it's perfectly suited to illustrate heat mapping procedure. But first of all, whale monitoring, I hope you agree that this is an important topic because whale populations are threatened by commercial whaling, ocean warming, and competition for food. So it's important to monitor whales in their spatial temporal migration. For example, if you see differences in their migration or something, or if there's something wrong, you can react. So otherwise, you might not even know. And this is done by looking on many photos, many taken from tourists, and specific whales are identified in these photos. And this is currently still done manually, and experts look primarily at corners of the fluke, as illustrated here. For example, they look at the shape or special features such as scars or color patterns. And to find an automatic solution for this task, a Kaiger challenge was created a few years ago, in which several thousands of whales are to be assigned with only a few pictures. So you have several thousands of these fluke images, several thousands of whale IDs, and for each ID you have only a few pictures. And it was not surprising that the 3 winning solutions were neural networks. And what we did is we took one of these neural networks to analyze it more deeply. And then we can formulate the following research questions. So why does the network identify images as the same way or a different way? And is a whale expert looking at the same area and image as the network? And the reasons why we want to find it out, first of all, because it's interesting to know. But also is the network behaves similar to a whale expert who can exploit the domain knowledge in a much better way. So for example, we know that scars can change over time. So if a network looks at specific scars, it might not be a good relevant features for the identification. Yeah, and based on these research questions and so on, I want to show you some interpretation heat mapping methods. The first one are occlusion sensitivity maps. They have a quite easy to understand and basic principle behind it, but they're quite powerful and generally already give you really good results. The goal is to evaluate the sensitivity of the trained model to occlusions by calculating the difference between the original score and the score after applying occlusions. So what you do is you have a network, a trained network, which this can be treated as a black box. And then what you normally do, you have an image and you get a specific score, in this case for a specific whale ID. So you store the score, you keep this in mind, whatever, and then you cover up systematically in the input image parts of the image systematically, and then you record or you store how much the score changed. So this is illustrated here. So you take the difference, and based on the difference for each part, you get such a heat map, and this heat map here is overlaid over the image. So illustrated here is this a little bit more into detail. So this is the heat map overlaid over the image. What you can see in it are green values and purple values. Green value means as soon as you cover one part up, the score decreases. That means that the regions are an indicator for a specific whale. So it was bad to cover it up. That means it was important for the decision. And then there are also purple values here, for example, in the back, you can see them. It means if you cover something up, the score increases. It's the interpretation and or the explanation what it actually means is a little bit more challenging because it depends on the loss function. For example, if you have a softmax loss function or a sigmoid loss function. Overall, it means that the regions are an indicator for other whale or not a specific whale. And then you might ask, okay, I'm talking about occlusion, but how do I actually occlude? And this is difficult to answer because it's not that you can really occlude or delete something in the image. As before with the Shapley values, it's not that you can just take it out because then you would have a hole in the image. It doesn't make sense. So you need to think about how can I cover up a feature but without adding an additional signal. And typical things what is done is, for example, you have a fixed value patch. For example, if you have a white patch, you cover up with 1 for the whole image. A little bit more sophisticated is when you take the mean value patch, because then it more blends more into the image, but you destroy the actual features in the specific area. Similar to this is this Gaussian blurring, or you can also just add noise in a specific area. Or you're not restricted to a patch. You can also use segments, and then you fill the segment with a specific value. So these are some commonly used strategies for occlusions, but you need to decide what is most appropriate for your task if you want to use it. And to show you some results, so what you see here is these are 4 images. All these 4 images show the same whale at different points in time, and these are the occlusion sensitivity maps for this specific whale ID. And what you can see is the occlusion sensitivity maps reveal that the fluke tips, these outer parts of the fluke, are the most important for the algorithm to identify this whale as this specific whale ID. And to summarize the advantages and disadvantages, first of all, it's very simple. So you just cover up and see what changes. It's very similar to what I already showed you regarding feature importance. And it's very versatile. So you have you can use it with every model you can think of, and you can also make some changes, what to include, how much to include. But this is also a challenge. So how to define the patch? So what to cover up? First of all, the patch is agnostic to semantic segments, which can differ in size. For the whale, for example, it might happen that a whole big part, let's say half of the fluke, is important, or small scars. So actually you would need different sizes of patches, but normally you cover up with the same size. Then every occlusion is a signal. So it's not that you just can delete a part of an image. So, you have the problem of distribution shift. So the patch, the covered up, not the patch might be out of distribution. With patch, I mean the whole image. And when you cover something up, this might be out of distribution. It means that, so the changed input is no longer in the data distribution we trained the model on. So we generally assume that the model will be evaluated on data coming from the same distribution as the training samples. And if this is not the case, for example, if we change some pixels so that the whole image gets very untypical, then the model output can be wrong and misleading. And it's computationally expensive because you need to cover up everything, and depending on how long the inference in your model needs, this might take a long time. And in order to decrease the burden of choosing a proper patch a little bit, and to get a more comprehensive result, for example, where mask cover image features or different sizes, there's a different approach called randomized input sampling, short RISE. And this can be seen as an extension to the occlusion sensitivity maps, or just a more comprehensive approach to it. So what is done here is that random masks are generated, and I will tell in the next slide how they are generated. And random masks are used to dim the image signal. And this is done by multiplying the image with a mask, which has value between 0 and 1. So this is illustrated here. So what you have is you have your input image here, and then you have these randomly generated masks here. And then you occlude the image. So you blend these masks into the image so that some parts are covered up. So before we had only one mask and we analyzed the result, but here we used several of them. And the saliency map is a linear combination of the masks where the weights come from the score of the target class corresponding to respected mask inputs. So this is illustrated here. This is a weighted sum, so it's a linear combination. Here illustrated are the scores, and this is a black box machine learning model. And yeah, so it works a little bit differently than occlusion sensitivity map, but this is how you combine all the mask information, what is actually happening with the score. So white in this image here means 1 and black means 0. And so if the score stays, then the important parts are still in the image, so it gets a high weight. So this is the crucial thing here, and how this is combined. Okay, so in the end, you get something like this. This is also one thing. Before we illustrated the heat maps in purple and in green. A more commonly used illustration of heat maps is here with red and with blue. Again, it also depends what are your preferences, and also it depends on the expert or the user you want to show this result. And as I said, let's have a look a little bit more into mask generation, because this is not so easy and there's a principle, a computation behind it. So first of all, masking, so what is the problem? So masking pixels independently may cause adversarial effects. I already talked about it. That means a slight change in pixel values may cause significant variations in the model's confidence score. Also, you want to have a quick computation, of course, and you do not want to have, so you want to have a quick computation with not a super massive amount of mass, so it makes sense to cover up, patch it in a meaningful size and not only random pixels. And to address these issues, what they did in their paper is they first sample smaller binary masks and then upsample them to a larger resolution using bilinear interpolation. And so bilinear upsampling does not introduce sharp edges and results in smooth heat maps. So this is what you can see here. So you do not have sharp edges, but it's more like, it's like more smooth. So what is done here, so first of all, you sample B binary mass, so say HB times WB, so they're smaller, by randomly setting each element either to 0 or to 1. And then you upsample with bilinear interpolation all mass to this specific size here. And so HI and WI is the size of the image. And then you can already see this is a little bit bigger. This is a little bit more bigger than the original image size. So the mass would be bigger. And then what you do is you crop areas from it with uniformly random indents. And so the actual size is from, or what you do is you do it from 0 up to this specific size. So you can imagine it like, okay, you have your image and then you have a mass which is a little bit bigger, and so you make random cropping in it, and then you take this mass for your approach. Okay. So now what is actually the difference between these two approaches? First of all, RISE reduce the burden of selecting an appropriate mask, because this mask generation is quite sophisticated. You have different patch sizes, what you cover up, and you have multiple ones, so you combine it, so it's more comprehensive. Yeah, it also takes a little bit longer, or it might take a little bit longer for computation. Then occlusion sensitivity maps with small patches are prone to adversarial attacks. This is also what I said before. That's why they have these more complicated mask generation process. And yeah, but the challenge of the kind of masking remains. So for RISE, it's the same. It's use 0 and 1, but still, it's not that you can just delete a signal. So you still have a signal, a covered up signal in the image. Okay, just to show you some results. So again, you have these 4 whales with these images. It's the same whale, and these are the results of RISE. What you can see is, you can see some patterns. For example, again, you have the fluke tips, which are highlighted. Also the top part of the fluke. But you also have some, for example here, some more noise in it. It might reduce if you use even more mass, but then of course the computation time increases. And again, for comparison, these are the occlusion sensitivity maps. Don't be confused by because of the different illustration. So red here is the same as the green here. And what you see, occlusion sensitivity maps are not so noisy, but they might, they might miss some smaller or larger patterns which are important for the decision process. Okay, and you can go one step further and analyze not only single heat maps, but also the whole decision process by analyzing all heat maps together. So this is again an extension. Today we are talking about local method, but this is an extension to get some global insights for the whole data set. And this can be done by performing clustering of the heat maps. And the goal is then to identify patterns in the decision process of the model. And with patterns, I mean that the cluster highlights and separates different features. Okay, so what are you doing if you want to perform such a global analysis? First of all, you extract heat maps from samples of interest, and then you vectorize the heat maps. So because it's really hard to you cannot cluster images. You need to vectorize them, unify their size. They need to have the same length, and reduce their dimensionality, because of some dimension you just can get rid, mostly the corners of the images, because they do not really contain information. Then you perform spectral clustering, and then you make an eigengap analysis. Eigengap analysis, I will talk about it in the next slide, what is spectral clustering, because spectral clustering includes an eigenvalue decomposition, and based on this you can perform an eigengap analysis, which is nothing else like you analyze the eigenvalues, and when you have a large gap between two successive eigenvalues, then you make a cut so you can determine in a quite comfortable way the number of clusters. But the important part is the spectral clustering. And so what is spectral clustering? It's a really cool tool you can not only use in this context, but also for other contexts. In other contexts, so spectral clustering clusters the data based on the similarities to each other. And for this we need a similarity matrix. And this matrix W, illustrated here and here, this matrix W can, for example, be derived by using a radius around each point or a k-nearest neighbor approach. So what you can see here is a data set, and the numbers indicate the data points. And for example, when you look at this point here, the fourth point, you take a radius around the point, and then you can see that the point 3 and 5 is within this radius. And the similarity matrix also shows this. So you have if you go here in the fourth row, because it's the fourth point, and then you have the third point and the fifth point actually have an entry non-zero, and that's why, because they are in the proximity in the closer surrounding of this point. So this is how you get the similarity matrix. For the k-nearest neighbor, it's similar, but here you need to be aware that the matrix is not symmetric, but we need a symmetric matrix. And so what you do is you additionally need to make the matrix symmetric, for example, by transposing it and taking the maximum. Yeah, and then what we need actually for spectral clustering is such a diagonal matrix. And this diagonal matrix is derived by summing W over all rows, and then you take this as a diagonal matrix. And then if we take the difference between diagonal matrix and the similarity matrix, we get the Laplace matrix. And based on this Laplace matrix, we make an eigenvalue decomposition and the clustering of the eigenvectors. So what you normally do is, when you have the eigenvalues and the eigenvectors, so you can cluster the eigenvectors, for example, with k-means, a very simple clustering algorithm, and the eigenvalue, as I said before, you can use for the eigenvalue analysis in order to determine a good number of clusters. Okay, so this is the result you can get from it. So what we specifically did is that we computed for each test image the heat map which belongs to the highest score. This might be a correct decision or not, and then we cluster them. And so what you can see on the left here, the left shows the whole fluke is important, which could be an indicator for the shape. So you can see that the heat map, the green, is over the whole fluke. In the middle, you can see there's the pigmentation near the fluke tips is important. And on the right, you can see that no specific features are highlighted in these images. And what we further did is we related now the detection rate to the heat maps. That means we computed how many of the heat maps belong to correct decision. And we were not too strict. We used the top 5 prediction, which is quite common in computer vision. And top 1 prediction means that the assignment of the highest score was also the correct one. Top 2 prediction means that the second highest score was the correct whale ID. And so on. And we count it as correct if it was within the top 5 predictions. And so what we plotted here is the cluster number versus the number of correct assignments, and the clusters are sorted with the number of correctly assigned whales. And what is interesting is, for example, what you can see here is you have a cluster which contains more than 90% of all heat maps that belong to top 1 predictions. And top 1, as I said, means the assignment with the highest score was also the correct one. It means if you have such a heat map, it can increase the trust in the results. So if you have a heat map in this cluster, you can say, oh, it's quite safe that I get a correct assignment. For some clusters, you have wrong predictions. For example, for these here. That means that the heat maps belong to test images that were not classified correctly. Overall, it turned out that some types of heat maps are associated with very high detection rates and some are not. And also that some cluster contains almost only correctly assigned values. This means that if the network is looking at certain characteristics of the fluke, that it can be said how reliable the network can detect these whales. And this was also our insight. So we also confirmed with a whale expert that some clusters can be assigned to high identification rates and that some patterns are more. That means some patterns, some characteristics are good for identification. For example, the shape of the fluke is much better than time variable scars. One thing is, so yes, the network did behave similar to a whale expert, but the whale expert normally looks at more than one feature. For example, a whale expert would not only look at the fluke tips, but he would also search for color patterns or maybe the shape of the fluke in combination. or some specific, not the shape of the whole fluke, but some specific part like the notch in the middle. Then we could confirm that the network looks at the right features, so there was no clavance effect. A clavance effect in this case would be, for example, if the network always looks into the background, not at the fluke. And imagine as a long-term goal, like a real-time evaluation of a photograph. So imagine you take a photo and it's sent to a database and the heat map is analyzed, and you could get an immediate feedback how good your photo was and how helpful, and if it might contribute for the spatial temporal monitoring of the weights or not. Okay, as a last example, I want to show you the local interpretable model-agnostic explanation, short LIME. This is interesting because it's a bit different. So it's nothing with covering up. It works with local surrogate models. The goal here is to interpret individual prediction by approximating the prediction with a local surrogate model. So this is illustrated here. So have your machine learning model, black box model, something is happening and you want to analyze one specific prediction. So you do not have a look here anymore, but you have a local surrogate model which is easy to interpret. A local surrogate model is generally a simple interpretable model used to explain individual predictions of intransparent machine learning models. So what is the basic procedure? You have given your intransparent model and you can get a prediction as often as you wish. And your goal is to understand why the machine learning model made a certain prediction. LIME tests what happens to the prediction when you give variations of your data into the machine learning model. So let's focus on one data sample, here the red dot. And what happens now is that LIME generates a new data set consisting of perturbed samples and the corresponding predictions of the intransparent model. So here the red dot is the original sample, the black dots are perturbed samples, and the plus and the minus indicate if it would is it still classified as the same class or another class. On this new dataset, LIME then trains an interpretable model. So this is the green line, and it's straight, and so it indicates it's much easier to interpret. And this is weighted by the proximity of the sampled instances and illustrated in black to the instance of interest illustrated in red. So this interpretable model can be anything what is easy to interpret. And the learned model should be locally a good approximation of the machine learning model prediction, but it doesn't have to be a good global approximation. And this kind of accuracy is also called local fidelity. So this here is only a good approximation actually in the vicinity of this red point. So again, what is the basic procedure? So first of all, you select an instance of interest, then you perturb the data sample and get the prediction for these perturbed samples. Then you weight the perturbed samples according to the proximity to the instance of interest. Then you train an easy to interpret weighted model on the dataset with the perturbed samples, and then you use this local surrogate model for interpretation. But we work with images. So what to do now for images? You need to somehow perturb your samples. What we use for this is superpixel segmentation. So superpixels are compact segments in an image, and here you see one of such an example of a superpixel segmentation. And what the important part here is now one superpixel in this image is treated as one feature. And what I mean with this, you see exactly here. So the next step is the input data permutation. So remember, one image, one superpixel segmentation. Doesn't change. We will now work with this. First, what you do first is you create a vector set here, where and the length of the vector is the number of superpixels, and each position in the vector exactly belongs to one superpixel. Then you randomly set the positions in this vector to 0 or to 1. And 0 means nothing will happen to the superpixel. So remember, you have an exact association between the position in the vector and the superpixel. 0 means nothing will happen to the superpixel, and 1 means that the superpixel will be covered up, for example, by 0. So here I illustrated in red. It's just for illustration purposes, but what you do is thinking about what you already learned about the occlusion sensitivity map, you cover up this random set of superpixels. And then you classify the image with occlusions to get a label C, this here. And you do this for many images. And with images, I mean for a lot of randomly sampled set vectors and covered up images. So what you get from this is if you do this many times, to be more specifically m times, you get m of these pairs. So you have a superpixel or this set vector where the length is the number of superpixels, and you have a label, an estimation. And this is your artificial training data set. And again, one superpixel is one feature. Again, what you need to do afterwards is next step is the weighting of the artificial instances, and again, one image is represented by the vector set m prime. So this is one perturbed sample, and now because these are images, it's a good idea to use the cosine similarity, the cosine distance between each perturbed image and the original image. And the higher the similarity between a perturbed image to the original image, the bigger its weight and its importance. And the last step is now you have this data set, you have the weights, and now you fit an interpretable model like a linear regression model using the weighted artificial data points. For example, if you use linear regression, you get the estimated coefficient of each feature, and then you can compute the effect. This is what I told you in the very first lecture. Or for example, you can train a decision tree, and then you can compute the feature importance, because one superpixel is one feature. You can use all the methods you already learned, which can be used for feature to get the feature importance with inherently interpretable model. And once you identified which superpixels are important, you can highlight them in the image, for example, like this. The advantage is, first of all, the local surrogate model can be derived based on the preferences for users. If you like linear regression, you can use it, or a linear classifier in this case, you can use it. If you like decision trees, you can use it. That's good. Also, it's good that it works for diverse input data, for images, for text, for tabulate data, and so on. So this is also not the case for all interpretation tools. And the reliability of the interpretation can be seen as the approximation ability of the surrogate model. When you know the surrogate model is not really able to approximate what's happening there, you might question the reliability of your interpretation. But again, you have hyperparameters. So for example, the sampling settings and the sample weights highly influence the results. To conclude, So what I showed you in the second part of the lecture were heat maps. And heat mapping is one of the most commonly used interpretation tool. It's an intuitive visualization of feature or more specifically pixel importance, and it's an easy to use tool for arbitrary models. So you can, it's model agnostic, and it generally works with a lot of models. But all these methods I showed you have hyperparameters, and it's crucial to tune them and to try several of them, because the result might change a lot if you do not if you do not choose them appropriately. It might be misleading. And an open research question, also one of my research area, is to to work on the usefulness of for scientific images, because, for example, not always you have these foreground background separation, so this object on a background. In satellite images, for example, you have areas but not specific objects. So yeah, it needs to be tested how useful these approaches are. With this, thank you very much for your attention, and there will be another lecture, the next one, which is about gradient-based methods and concept discovery. So stay tuned and see you in the next lecture. Thank you.